This year's prize is about creating new rooms for chemistry.
What does that even mean?
New rooms?
New rooms for chemistry.
Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i kemi till Susumu Kitagawa, Kyoto University, Japan.
All right.
Richard Robson, University of Melbourne,
Yo, Omar!
Australian.
Omar Yaghi, dude,
Omar
from the
Yaghi,
prediction. I knew it.
That's amazing.
I told you.
Yep.
Yes, I called
it on Sunday.
Called it on From First Principles podcast, baby.
That's so funny. Hello, Internet. This is your captain speaking, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. We are day 3 of Nobel Prize week, chemistry. We just watched the live stream, and the winner is Metal Organic Frameworks, which was part of our prediction on Sunday, a branch of reticular chemistry. And so we're going to dive right into understanding what are metal organic frameworks and why this is so important.
Yeah, I mean, so the chair of the Nobel Committee said, new rooms for chemistry,
New rooms
right?
for chemistry.
We're like, what are you talking about? Well, it's a pretty good way of talking about metal organic frameworks, okay? What we're doing is we're making new rooms for chemistry that have custom sizes, custom doors, and they're made out of custom walls. So they've got a cartoon, as they always do. On the left there, that's the cartoon from the Nobel Committee.
Yes.
And on the right is the actual one of the examples of a chemical compound that exhibits this metal organic framework. Okay? And the idea is these things are exceptionally useful, mainly because they got a bunch of holes. Okay? They have a bunch of like vacancies that you can use to do really cool things. For example, suppose you want to filter out carbon dioxide from exhaust, right? This porous material can now do that, right? Suppose you want to like get water from thin air. The porous material can now do that, right?
Yes.
Because you're making holes that are the size of the chemical compounds
that you're looking to,
or like that are going to interact with the chemical compounds that you're trying to extract or you're trying to catalyze. Things like that. So it's like you can tune the building material, right?
To what
using these metal organic frameworks.
It's like I built a resort, and each room is custom built for each guest that I have at the resort.
Yeah, and you can now build each thing.
Right?
Because it's effectively like really, really complicated Lego blocks. Okay. If the Lego blocks individually are like atoms and small molecules, now we're creating like structures that you can then just like attach.
That makes sense.
And make like buildings.
Yes.
That can fit whatever molecule that you want. Right?
Okay.
It's really cool. So the award was given to these 3 individuals for basically starting this field. And like bringing it to its heyday. So the first one is Richard Robson. He's the one in the middle from the University of Melbourne. He's the guy who sort of founded this back in the 1980s. And then there's Susumu Kitagawa from Kyoto University and Omar Yaghi. They, in parallel, brought the field forward to where now it's like so many industrial applications, right? I think it's very cool. I've been doing a lot of research. I was a little bit better prepared this time because I did have the prediction, but it was still like getting into the weeds. It was really cool to see how the history progressed.
Right.
Okay. So chemistry has been really good for a very long time with something called zero-dimensional chemistry, okay? Zero-dimensional chemistry is like something that is localized, okay? Like even the buckyball or like small molecules, right? Those things are in some sense zero-dimensional because they're point-like, right? And that's a zero dimension.
Right.
Then we started getting really good at 1D, right? Polymers, that's a carbon nanotube. And we wanted to get to 2D and 3D, okay? But that was known as kind of a synthetic wasteland because it was really hard to figure out how to create stable 2D and 3D structures. 1D, you can imagine, right? You just like, add like in a chain of like nerd, like, those nerd ropes?
Yes.
It's like that. It's like relatively easy, okay? Compared to the 2D and 3D stuff that this Nobel Prize is going for. But there was a precedent to try and find these things, okay? There are these minerals that are found naturally. They're called zeolites. It was discovered by the Swedish mineralogist Alex Cronstedt in 1756. And what he did was he observed that like if you take this material, right, which in this case it's stilbite. Zeolite is the class of materials. What he discovered was this particular one. This thing could absorb water, okay? And then when he heated it up, steam would come out. Okay, very simple observation. But what does that mean? That means inside the chemistry, it's trapping water molecules, right? And then as you heat it up, those water molecules are going away in the form of steam. So what that means is there's some ability of this thing to absorb chemical compounds and then put them out, right? And there's like holes inside where this water molecule is going, right? And that's why he coined it zeolite, because zeo is Greek for boil and lithos for stone. So it's like a boiling stone. And these zeolites became like a big passion of chemists because they're found naturally and you want to try to characterize them. The next thing that kind of gets into this is the Berlin blue, which is this pigment that was discovered in the 18th century. It's got a relatively complex structure. Like on the right-hand side, you're seeing the structure, which is basically a bunch of iron, which is iron ions. So iron 2 and iron 3, that means it's either 2 electrons are gone or 3 electrons are gone. And then inside, they're linked by these carbon-nitrogen bonds. Okay. And now we're starting to get into metal organics, right? Metal, the iron, organics, anything that has carbon. This is the like day zero. Okay. And on the left, that's the famous Great Wave off Kanagawa. The print by Hokusai in the 1800s. Right. That blue pigment is the Berlin blue. Right. The Japanese printmakers would like import this from Europe because making blue was incredibly difficult. Like the Egyptians used to make blue and then we forgot how to do it because like the Egyptians.
That's such a crazy, knowledge is forgettable.
Yeah, knowledge is very fragile, dude. If you're not careful,
right, and actively keeping it up. It's funny, that same blue wave. My wife has a Snoopy bag she got from the Snoopy store in Japan with that blue wave on it. So I'll tell her that fun fact.
Yeah, it's pretty cool. So and that is like the day zero metal organic framework that sort of led to all of the developments and then created the Nobel Prize today. So we know that these things are possible. Right?
Because they occur in nature.
Yeah, they occur in nature. The idea is we want to be able to engineer and very specifically put stuff together, okay?
In order to basically get the emergent properties that we're looking for.
Yeah. And in order to figure out exactly how we're going to do this engineering, we need to do a little bit of basic chemistry. Always, you got to start from first principles. So we go to 1913. Alfred Werner wins the Nobel Prize in 1913. He basically starts this field of coordination chemistry. Okay, he starts thinking about metal ions and how metals can bond covalently with other atoms. And he characterizes these tetrahedral complexes. Tetrahedral meaning the like four, tetra meaning four. So 4 bonds that are in this like sort of nice crystalline pyramidal structure. And these bonds between the metal atom and the other atom is what's called a coordinate bond, okay? And this is different from a covalent bond. So if you go to the next slide, I'll show you what the difference is. So in a normal covalent bond, you've got shared electrons, right?
Yes.
In O2, for example, oxygen and oxygen, each oxygen is sort of donating an electron to the bond to create the O2 molecule. Same thing with CO2, H2O. With a coordinate covalent bond, there's only one donor. Okay, the other guy's kind of leaching. Okay, so over here you've got, on the left-hand side, you've got the yellow atom that's got a full shell with 8 electrons.
Yes.
And then on the pink atom has two holes.
Right.
So the yellow atom goes in and donates. Now everyone has full electron shells and everyone's happy. This is called a coordinate covalent bond. Okay. And this is going to be the sort of building block of the chemistry that we're about to talk about, that won the Nobel Prize, okay? Because metals make ions, right? And what ions, usually with metals, the outer electrons, which are in the D shells, that are like far away from the nucleus, they're just gonna go away.
Right.
So you're gonna get like a copper ion, which is Cu+, that means 1 electron left, or the ones we were talking about, iron 2, iron 3, that means 2 or 3 electrons left. So they got these holes. But now other atoms can come in and fill that gap, and you get a coordinate covalent bond. right? And that's going to be the building block for the chemistry that we're about to talk about.
Yes.
Okay? So
Yes.
with that in mind, let's go into our Nobel laureates. So first we got Richard Robson. He is in the University of Melbourne. He's teaching classes in 1974. And this is a great example of how teaching actually leads to discovery. Okay, so he's teaching, and he needs. You've probably seen these in like high school chemistry
100%,
classes, right?
yes.
The balls that have like holes, and then he puts sticks in it to make molecules. So he's trying to get those made in the wood shop.
Okay.
Okay, so he's sending over instructions on where to put the holes, because each atom is going to have specific geometry on where the holes go and where the atoms are being made. And as he's doing that, he needs to mark out where the holes are. He gets inspired by this, and he's like, wait, if the holes in the atoms tell me the geometry of the bond, right? But these holes can be on the outside of bigger molecules, and those holes will still preserve the geometry, right? On the outside. And he was inspired by the diamond, which is, we've talked about.
Yes.
In the next slide, we can look at the crystal structure of the diamond. That's a tetrahedron. It's carbon.
Right.
With the carbon, you've got 4 holes that you make, right? Which is one on the top and then 3 sort of pyramidal ones on the bottom. And then you can connect all of these together to create a tetrahedral crystal of carbon, and that's what a diamond is. So he was inspired by this, and he's like, okay, if I want to create a diamond-like thing, but I want to do it with bigger building blocks. Right. Can I do that?
Right.
Okay. So he decided to try the copper ion, which is Cu+. And with the copper ion, he attached copper ions, so 4 copper ions. He attached that to a molecule that already had this tetrahedral geometry. Right. The molecule is called 4,4,4,4 tetracyanotetraphenylmethane. Okay, this is one of the reasons why I never really got into chemistry in high school. Is like the names were just ridiculous. But the main idea behind this molecule is it's pretty rigid. Right. Okay, it's a rigid molecule, and on the ends of that pyramid, the top and the 3 ends, there's something called a nitrile group, which is this CN, carbon and nitrogen. Yes. And those things really like bonding with copper. Okay, so what you can do is put 4 copper ions at the points of this pyramid, and then those 4 copper ions can then bind to the next pyramid and the next pyramid. And what you get is this very nice crystalline framework. This is the first metal organic. It's not really organic, but it's the first sort of idea behind like creating a metal crystalline structure using metal ions and other stuff in between. Yes. And it had a bunch of holes. Right. Remember? Right. It had a bunch of holes. And he published this in the American Chemical Society in 1989 and 1990. And this was very unexpected at the time. Right. Okay? Right. This was like very, very cool, because people used to think like, oh, like if I just put together metals with this other kind of stuff, I'm going to get a molecular bird's nest. Right. Bird's nest is like very kind of disorganized. It like maintains its shape. Right. But it's not this kind of regular sort of thing, right? Yes. This was very cool when it first came out. And at the same time, he also started talking about the predictive framework in how to design these 3D molecules. Right? Like what are the rules that are sort of needed to put these Lego blocks together and have them be sort of stable. Okay. He also at the time he started talking about the future of applications. He's like, this could be used in the absorption of gases, catalytic reactions. So he was very forward thinking, right? And it sort of started a lot of people along this track. Right? And two of those people are
he opened the door. Yep. For other people to think in this direction as like, oh, there's a there. Yes. That's worth study and exploration.
Exactly. Yeah. It was still the stuff that he made was still kind of rickety, and it tended to fall apart. Right. And this is where Kitagawa and Yaghi come in. All right. Yes. So now we're going to go to our second Nobel Prize winner, Susumu Kitagawa, and he makes this. Okay. So this is in I think 1995. He publishes this, and it's a tongue and groove where he's using cobalt, nickel, and zinc ions in a 3D framework, and this is really stable.
Okay.
Okay?
Yes.
This is the first sort of like nice, stable thing. You make this in water, okay, in a soluble sort of chemistry. That's how this thing is manufactured. You've got like these grooves that are like cross-linking to each other. And the trick is, if you dry it up, it's still stable. And it can also be used and reused to absorb gases and then let them out then absorb more. So it's a stable compound. It's not like it's a true catalyst in that sense, right? It's not getting used up.
It's not a single use or like a limited n number of use. It is structurally going to repeat the same process every time.
Yeah, and it's sturdy to that kind of thing, right? So this is the first demonstration of a reversible gas adsorption.
Okay.
Adsorption meaning like at the surface you're taking in the gas, as opposed to absorption with a B, which is just like a volume absorbing. Okay, adsorption means like a 2D kind of thing.
Yep.
Right. And so he gets really big on that. At this point, it's still he actually had a lot of trouble trying to get funding to do this kind of stuff.
Interesting.
Because people were like, oh, zeolites already exist. They weren't really convinced that the stuff that Robson was doing was going to work because it was so rickety.
Yes.
Right. It was just this kind of like fringe thing. But he was at Kyoto University at the time, got his PhD, and then he got a lab there, and he finally started making these things work. Okay. And the thing that really convinced people was the porous crystal that he made.
Okay.
That's the next one.
Okay.
The porous crystal that he made, and that's Kitagawa on the right. The porous crystal that he made was soft in the sense that it deformed and changed its shape based on whether it had stuff inside in those cavities. Okay? So now this is something that zeolites can't do. Right? The natural occurring mineral are extremely rigid.
Right.
But you've got this thing where like it can like the bonds are flexible. So if there's nothing inside, now you can imagine, right? Like creating these those toys where you got a magnetic ball and like the stick.
Yes, I know exactly
you know what I mean?
Yes.
Yeah. It's like those things can like move around, right? And this is doing the same thing. So this was very big, right? It was expanding and contracting like a lung.
And again, the dynamic structural behavior is the key difference here to the naturally occurring zeolites.
Stuff. Yeah. And so this was the first clue that it was like new chemistry.
Right. There's something there was a more fundamental understanding that could be gleaned from continuing to go down this thought.
Yes. And creating like way new materials that you definitely can't find.
So the material science implication became more obvious.
Yeah.
Fascinating.
Pretty cool. And in parallel, we've got Omar Yaghi.
Yes.
Okay, Omar Yaghi has an incredible life story.
Which we talked about a bit on Sunday.
Yeah. It's he was a Palestinian refugee in Jordan with his family, like very poor. The entire family lived in a single room, but he got really into chemistry at the age of 10. He came to the States for higher studies, got his PhD at University of Illinois, Urbana-Champaign, and then he started really getting into these metal organic frameworks. Okay, he was like, this could be something, right? He got really interested in that, and at Arizona State University, that was his first faculty appointment. That's when he publishes this 2D molecule that can hold stuff, and it can remain stable up to 350 degrees Celsius.
Oh,
you can heat this thing up, and it can still hold its stuff, and not get completely degraded.
Right.
He published that in Nature.
Yes.
Okay. So this was the first sort of big thing, right? Yes. He starts making a name for himself, and in 1999, he publishes the big one. Okay, this is the big one. This is the sort of classic example of metal organic frameworks. Okay, and there's posters of this in every chemistry department. Okay. This is called MOF 5, Metal Organic Framework 5. It's got a zinc at its center, then oxygen molecules in a pyramid. Okay, that creates a little pyramid. You attach 4 of those pyramids together with carbons on the end, right? And you get the middle thing, which is 4 pyramids together to create one giant sort of diamond type thing.
Yes.
With carbons at the end.
Right.
And that carbon is key because now we're getting into the organic.
Okay.
With those carbons at the end, you can now start attaching linkages to other diamonds, other blue diamonds, and start creating cavities. This was the MOF5 molecule, okay? And this thing was insane. This thing was like 3,000 meters squared of surface area per gram. That's the thing I was when we were talking about it on
Sunday,
our predictions. Right. It's a single gram of this substance is going to have enough surface area of like a football field or like several football fields.
So crazy.
Right? It can absorb a lot more than zeolite can because of that. Because of that thing.
Yes.
And also, it's again stable until 300 degrees Celsius.
Right.
So it's resilient.
Yes.
It's pretty simple to make.
Yes.
And it's
hugely functional.
Hugely functional.
Yeah.
Right? Yeah, exactly. The possibilities are endless, right? And this is the field that introduced sort of reticular chemistry.
This is the beginnings of it.
It's like using modular components to make these crystalline lattices, right? Okay. It was Yaghi and Kitagawa together that sort of figured this whole thing out. And Yaghi went even further. So in photo 16, you'll see he takes the MOF, which is the one on the left, and he figures those linkages, right, between the carbon molecules, between those carbon atoms
that are on the edges,
that are creating this cubic cavity. Those linkages, I can just make those linkages bigger.
Okay.
Right? And then I'm going to have more space.
Yes.
It's so simple.
Yes.
The linkages are organic molecules that are made out of carbon rings attached to carbon rings attached to carbon rings. Well, I can just start adding more and more carbon rings.
And now you're actually increasing that surface area of available space.
Yes. And what you can do is you can have customizable size of the pore. Right?
Yes.
By saying, okay, I have 3 carbon rings.
Yes.
The pore is going to be this size. I add 6, then it's going to be a little bit bigger. So whatever chemistry you want to do, do you see now?
You can build for exactly the size and like exactly the parameters that you need. And so this is really the dial that you can turn.
Yeah.
In order to get to the outcome that you're looking for.
Yes, exactly.
Fascinating.
Right? And now this is when this is when things got really big. He published those 2 papers in Nature and Science, and those are basically the papers that won the Nobel Prize.
Got it.
Okay, it's the papers from Robson, Kitagawa, and finally the Nature and Science papers.
That's and I totally get your point about the implications of the linkages being malleable in terms of their size and how that creates more available potential space.
Yeah,
that's usable.
Yeah. It becomes totally customizable now, right?
Yeah,
now you literally have
it's programmable.
Yeah, like things
you can engineer properly.
You can engineer completely properly. Okay, and so he started out at University of Arizona.
Yes,
and then he moved actually to UCLA.
Yes.
In 2012.
Yes,
because by this point, I think everyone knew he was going to win.
Yeah, right.
The Nobel. Okay,
right.
So now institutions are like
Berkeley.
No. First he moved to UCLA. First he moved to UCLA.
Okay.
Actually, no, you're right. So I got the year wrong. I think it was 2005 or 6 when he moved to UCLA. Okay,
that's how he got to California.
Yeah, and then that's how he got to California. And then he was in the chemistry department at UCLA.
Yes.
And then in 2012, Berkeley was like offered him an offer he can't refuse.
Of course,
because Berkeley was like, okay, he's definitely winning by now,
right?
and we want that +1,
100%.
So he moved to Berkeley in 2012. He became the director of the molecular foundry at the Lawrence Berkeley National Lab, co-director of the Kavli Energy Nanosciences Institute, and just in 2025, earlier this year, he became a university professor, which is the top honor in the University of California, reserved for like the highest distinction. Well, so he was working his way up to like everyone sort of. That's why it was like kind of easy to predict
that it was going to be him because the signals were there.
The signals were all there, and but UCLA first poached him, and then Berkeley poached it from UCLA.
Like, no, that's ours.
Yeah, like
the UCLA, the little brother of Berkeley. In this context.
Exactly. Yeah. So it's like, okay, now I'm going to keep that one. And yeah, now he's won the Nobel Prize, right? And so these 3 people won the Nobel Prize. Right now, there's so many different applications to this metal organic frameworks. We're just going to go through a few of them. So this first one, these are 3 molecules. The one on the left, that's used to capture water vapor.
Okay.
Okay, the one in the middle, that can be used to catalyze the decomposition of crude oil,
Oh, very interesting.
right? Which is very nice for like environmental people.
100%.
On the right, that's something that can absorb PFAS, which is perfluoroalkyl. It's one of these like forever chemicals.
Yes.
The EPA always talks about it.
Yes.
Like they never degrade, get into our bodies, get into the environment. That's something that can absorb those forever chemicals from water.
So one of the ideas here is that we can begin to create these chemical compounds that we can then use for things like, controlling emissions issues.
Yeah,
dealing with
that's
rubber
actually
chemicals.
the next one.
Oh, beautiful. Yes.
Yeah, you're exactly right. The one on the left, that's for mining rare earth metals from wastewater.
Oh, okay. Yeah.
Right, because
yes.
like industrial waste is going to have a bunch of metals.
Yes.
And you don't want it to go into
that's a huge application.
Yeah.
That's an unbelievable application.
Right, and then in the middle, that's to absorb CO2.
There you go.
There you go. That's what you were talking about.
Yep.
And then on the right, that one's actually my favorite. That one can store and release hydrogen at normal pressure.
Oh, really?
Okay. So you don't need a tank of compressed hydrogen.
That's really
And
crazy.
that's huge.
Yeah.
Because compressed hydrogen
Yes.
is how you get the Hindenburg in your car.
Right.
Right? And like everything explodes. So nobody wants hydrogen fuel cells. Well, now with this kind of stuff, you can get hydrogen fuel cells.
I can understand why this won the Nobel.
Right? Yeah. And what you saw there is like all of these things have like pretty similar, you can see that they're the same chemistry.
Yes.
You know what I mean?
Yeah. They share sort of a similar substrate of structure.
Yeah. It's repetitive, it's crystalline, but each of the little tiny crystals, instead of being a single atom, now they're these giant building blocks, right? And the holes can be giant. In the world of atoms, these things are giant, right? You can do nanometers, tens of nanometers.
This is interesting because it's kind of similar conceptually to yesterday's prize in physics around this idea of scaling up to larger sizes with the quantum tunneling.
Yeah.
But in this case, with metal organic frameworks.
Yeah. It's an incredible field. And I just wanted to see what was happening nowadays. So they got AI going in on this too.
Of course.
They have a chat. They have a chat MOF.
Really?
Yeah, a chat metal organic framework where you like chat with it, and then it'll like generate. Like it's like I want a chemical compound that does this, and then it'll like spit out like, oh, you should try these things.
Chat
right?
MOF.
Yeah, they have a generative framework there for like generative AI can make photos.
Right.
Well, it can also, if you train it on the chemistry,
Right.
it can start making
Right.
these metal organic frameworks. And on the right, that's a news article from Berkeley. Omar Yaghi in his lab, he's actively using AI. And like one of his students, I think, came up with like 15 molecules in 6 months. just accelerating this process, right?
Yes.
It's pretty cool.
This is what we talk about a lot, which is, again, a lot of generative AI conversation, et cetera, revolves around consumer use cases, understandably, because that's where most people are actually using it currently. But there's not as much chat. I mean, we've talked about this. There's, generative AI for CRISPR. We have it for MOF. There's also things like AlphaFold. LIGO.
Oh, that wasn't generative, but
still AI sort of assisting and accelerating the process of research and discovery. And it has like real world implications.
Yeah.
In terms of us getting to these things quickly with fewer human capital resources, with less financial capital resources.
Yeah, it's also like a democratization process.
Yep.
Because people who maybe, chemistry labs who want to do something, right, but don't have the expertise of the metal organic framework can go to this chat thing and be like, hey, like this is the thing that I want to accomplish.
Yes.
Can I do it with MOFs? And the chat will be like, yeah, actually just make this, and this, and then put it in this way.
It's so crazy. I think there's this conversation happening. CEO of OpenAI, Sam Altman, yesterday or the day before, did an interview where he was asked about AGI.
Okay.
Because there's this whole AGI is near conversation.
Yeah.
And there's usually two sides of it where people are like, we're nowhere close. And other people are like, we're very close. And the signal that's being alleged as like why we're getting close is in these kind of research use cases, there is, AGI for some people is defined as like being able to have novel insight. And there are a couple now cases in these, again, research contexts where the models are actually having novel insights that are working. And not just working, like working really well. it's not AGI in the way I think people imagine it from the movies.
Yeah.
But, there's a glimmer. If these models can truly generate novel insights, even at small scales, that's hugely
huge.
That's
Yeah.
hugely important.
Yeah. That's gonna be crazy.
Fascinating.
Dude. Yeah. Well, and that was the chemistry prize.
So and I think there's so many implications for this more broadly moving forward.
Yeah, dude. It's gonna be it's gonna be very cool.
I want to take a moment. So we've talked about this is our day 3 of
The last
Nobel
day.
Prize week. So many of you, thousands of you, have sort of joined us for this journey. It's been an incredible week.
Yeah.
So thanks everyone for tuning in. We did medicine on Monday, physics on Tuesday, and then chemistry today. I wanted to do a quick tally about the winners.
All right.
Right? We're going to break this down in sort of two categories, institutions and countries. This is like our ESPN top 10.
Yeah.
So on the institution side, we had some unsurprising number one winner. So at the top with 4 Nobels is Berkeley.
Yep.
3 for physics, 1 for chemistry. Kyoto at 2. UCSB, unexpectedly, for me, 2. UCLA 1. Princeton got on the board.
We got on the board.
We got on the board with 1. Yale with 1. Princeton we're putting before Yale because we came first.
Yeah.
And then we have University of Illinois, Urbana-Champaign with 1. Oxford, Melbourne, Cambridge, and Paris Sud University, all with a single Nobel.
Yeah.
And if we look at it by country, number 1, big old America.
USA, baby.
6 universities in the US, 2 from the UK, 1 from Japan, 1 from France, and 1 from Australia.
Yeah.
So great representation.
Yep.
The UC system ran the board.
Ran the board, dude. California, baby.
California is continues to lead in sort of fundamental research.
Yeah. And this was the public institutions in California.
Right. Not the
I guess Stanford and Caltech didn't show up this year.
Maybe next year, guys.
Yeah.
Maybe
neither
next year.
did MIT or Harvard.
But Princeton's there.
Princeton's there.
Oh, goodness. Again, another just great episode. We talked about metal organic frameworks, a branch of reticular chemistry. We did talk a little bit more about this also in our Sunday preview. So if you're interested, go back and take a listen to that. But just an unbelievable. We'll definitely do this next year again.
Oh, yeah.
We'll probably have a little bit
so
more.
Much fun.
More going. We'll maybe get the Nobel Society to help us get some inside access.
Yeah.
I'm Lester Nare, your host, joined as always by my co-host and our resident PhD, Krishna Choudhary. Thank you all again for joining us for Nobel Prize Week. It's been an incredible week. We will see you all next week.
Nice.
All right.
That's a wrap. Big week.